In my last video, I made this slightly yellowed liquid called benzaldehyde from toluene paint stripper, and today I'm gonna turn it into something pretty surprising. It's a pharmaceutical drug called Phenytoin, an anticonvulsant that's been used for almost a century to treat epilepsy and seizures. Phenytoin is sold under the brand name Dilantin, and is a type of molecule called a hydantoin. This puts it in the same family as tons of other drugs such as dantrolene and even barbiturates. When medically administered, it acts on sodium channels in neurons, stabilizing them and preventing rapid firing, hence its use in epilepsy. And even though phenytoin is a prescription drug, it's not a controlled substance, and so the chemistry here is completely legal to demonstrate. That said, I'm not going to use it or distribute it, and this is strictly for educational purposes. While making a working pharmaceutical from paint stripper might sound complicated, the synthesis is actually really elegant and surprisingly simple. Now, for the first step in making benzaldehyde into phenytoin, I'll be doing a classic organic chemistry synthesis called the benzoin condensation. This reaction occurs between two molecules of an aromatic aldehyde, in this case benzaldehyde, to form a new carbon-carbon bond. The product is a really useful compound called benzoin, which has both an alcohol and a ketone like carbon. The reaction is catalyzed by potassium cyanide, which acts as a nucleophile and helps move electrons between the two molecules of benzaldehyde. However, cyanide is extremely toxic, it's regulated, it's a pain to store, and if you breathe any of the dust, this might be your last experiment. So instead, I'm going to be using something a lot less dangerous and a lot easier to get: thiamine, which is also known as vitamin B1. Interestingly, thiamine basically works the same way as cyanide here by forming a nucleophilic carbene that helps catalyze the reaction. It's even biologically relevant, and this mechanism is a big part of how enzymes catalyze very similar reactions inside your cells. Now, to get started, I needed about 4 grams of thiamine nitrate, and since a single capsule contained 500 milligrams, I went ahead and broke apart 8 of them and transferred the powder to a beaker. The more common thiamine hydrochloride is preferred here, but for some reason my pharmacy only had the nitrate salt. The main benefit of the hydrochloride salt is that it's far more soluble in water and alcohols, while thiamine nitrate has a hard time dissolving to any meaningful extent. However, this is pretty easy to fix, and to get it to dissolve completely, I next went ahead and added 50 milliliters of 0.25 molar hydrochloric acid mixed with 20 milliliters of methanol. The hydrochloric acid will quickly convert the barely soluble thiamine mononitrate to highly soluble thiamine hydrochloride. And after only a few minutes of mixing, all I had to do now was pass the mixture through a coffee filter to remove whatever fillers were present in the capsule. Meanwhile, I dissolved 1.2 grams of sodium hydroxide in a minimal volume of water, and then diluted this to a final volume of 10 milliliters. This roughly 3 molar mixture of sodium hydroxide was then placed on ice and allowed to cool below 10 degrees Celsius. As soon as the thiamine extract was done filtering, I went ahead and put the boiling flask on ice and added 75 milliliters of cold methanol. Under constant stirring, I next began to slowly add the sodium hydroxide mixture in order to deprotonate the thiamine and activate it. As the hydroxide is added, the mixture turns a bright yellow, and that's the active carbene forming. This activated thiamine is incredibly fragile, and so it's important to maintain a temperature below around 10 degrees Celsius during this step. Once the yellow color is constant, this step is complete, and the pH at this point should be somewhere between 9 and 10. I then measured out 25 milliliters of my benzaldehyde and began to slowly add it to the yellow mixture. You'll notice that as I add the benzaldehyde, the mixture lightens up somewhat, and I correct this by adding a few extra drops of the hydroxide. I'm not really certain whether the pH drop during this step is normal or because my homemade benzaldehyde contains some benzoic acid impurities. In either case, it's very important that the pH is still between 9 and 10 by the end of this step, and this can be indicated by the bright yellow color of the active carbene. You also might notice a precipitate form as more benzaldehyde is added, and I'm not really sure if this is benzoin or an intermediate. In either case, I eventually added all 25 milliliters of my benzaldehyde and then arbitrarily decided to add an extra 5 milliliters for a total of 30. After all the benzaldehyde was added, I allowed this to continue mixing for another 10 minutes, during which time the mixture turned an amber color along with a whole lot more of the precipitate. I decided to dissolve this by adding some extra methanol, although I don't think it was really necessary, and then I set the flask up in a hot water bath. The most important part of this step is to not raise the temperature above 60 degrees Celsius, and this is because the active carbene is very delicate and can easily decompose if it gets too hot. To help remedy this, I chose to use methanol over ethanol due to its lower boiling point, but an alternative is to simply do this step with no heating at all over at least 24 hours. Anyway, while this is doing its thing, I'll quickly explain how this all works. Now, the chemically active part of thiamine is the thiazolium ring, which forms a carbene after being deprotonated. The carbene next attacks the benzaldehyde, forming a nucleophilic intermediate that rearranges in such a way that the polarity on the carbonyl is reversed. In another nucleophilic addition, this reactive intermediate attacks a second molecule of benzaldehyde, which subsequently rearranges with a proton transfer and the elimination of the carbene to yield our final product. It's important to note that while every step of this reaction is technically reversible, the final product benzoin is more thermodynamically stable than its intermediate, and this pushes the reaction forward. Also take note that the thiamine is never actually used up by the reaction, and this is what makes it a catalyst. Anyway, after 90 minutes on the hot water bath, I went ahead and cut the heat and removed the flask. After only a few minutes, very small needle-like crystals of benzoin began to form, and I allowed them to continue growing overnight. If crystals don't start growing for you here, you can always try scraping the sides of the glass, putting the flask on ice, or simply dumping the mixture directly into an ice bath. Also, if you instead opted to do this step at room temperature, the mixture would have slowly become more viscous and opaque as much smaller benzoin crystals formed over time in the suspension. Neither method is necessarily superior, and after allowing the mixture to cool to near freezing, I simply dumped it directly into my Buchner funnel to collect my crude benzoin. If you prefer smaller fluffy crystals, this could have alternatively been dumped into an ice bath while still hot and then vacuum filtered. Anyway, to purify my crude benzoin, I first dissolved the crude product in a minimal volume of a 50-50 mixture of ethyl acetate and ethanol. Benzoin is soluble in both ethyl acetate and ethanol, but far more soluble in ethyl acetate. With that said, either of these solvents can be used alone, but I felt like using pure ethanol would require too much volume, while using pure ethyl acetate would hurt my recovery. In any case, I then let this cool back down to room temperature to allow beautiful crystals of pure benzoin to form. I got some really good footage of these crystals forming, but in the interest of time, I decided to put most of it later in the video. In the meantime, I eventually put the beaker on ice to cool completely before breaking up the purified benzoin crystals. These were once again collected by vacuum filtration before transferring them to a watch glass to dry overnight. By the next day, the benzoin was completely dry, and so I weighed it for a final mass of 21.88 grams, which represents a 72.9% yield. I think this is pretty good, particularly since I didn't have to use any cyanide to get here. The final product is this beautiful white crystalline compound. It melts around 137 C, which matches the literature value for benzoin. Now, you'll notice that the crystals are ever so slightly yellowed, and I'm not really positive whether this discoloration is due to using homemade benzaldehyde or if this is something from the activated thiamine. Regardless, it can probably be very easily removed by simply boiling the recrystallization mixture with activated carbon and then filtering it off before allowing the crystals to form. As a quick side note, before I did the reaction the way I showed here, I did a preliminary trial run using some extra benzaldehyde that I made by the oxidation of benzyl alcohol using nitric acid. In this first run, I very closely followed the formal procedure for this process, and so I didn't add any extra hydroxide as the reaction mixture lightened. I also heated the mixture directly on my hot plate and didn't allow the mixture to cool overnight. While doing it this way was way quicker, my final yield was only around 52%. One final fun little thing I found out about benzoin while filming this project is that it turns purple when dissolved in alkaline mixtures. To demonstrate this, I simply dissolved about 1/5 of a gram of benzoin in some methanol along with a few flakes of potassium hydroxide. After both chemicals had dissolved, you can see that the mixture is now a distinct purple color. But that's not the cool part. When I shake this flask aggressively, the purple color immediately disappears, only to reappear the moment I stop. This is probably the only organic redox demo I've ever seen that doesn't require an indicator, and I found it entirely by accident. Again, this could be some weird anomaly considering I'm only using homemade reagents here, so if you happen to have some pure benzoin lying around, let me know if this works. Anyway, now that I finally had benzoin, I next needed to oxidize it to something called Benzil. Benzil is a bright yellow crystalline compound that itself is used in photochemistry and coordination chemistry, but for today, I'll only be using it to make my phenytoin. The procedure is pretty straightforward, and the easiest way to oxidize benzoin to Benzil is by using nitric acid. Nitric acid is ideal for this reaction because it's a very strong oxidizer, and in this case, it selectively oxidizes the hydroxyl without tearing the rest of the molecule apart, as long as you're careful. However, nitric acid is also volatile, corrosive, and releases toxic nitrogen oxides as byproducts, so I'll be doing this step in the fume hood. To get started, I began by adding 21 grams of the benzoin to a flask, followed by 100 milliliters of 60% nitric acid. I began by stirring the mixture thoroughly for about 5 minutes at room temperature to allow the two chemicals to mix, and then transferred it to a boiling water bath in order to drive the reaction forward. I also connected a trap to the reaction flask in order to prevent this from possibly boiling over, but I don't think it was necessary. Once the reaction did finally get going, it was accompanied by the evolution of toxic red nitrogen dioxide gas. Most of this gas collected in the trap, which I thought looked pretty cool. Now what's happening here is a fairly basic oxidation of benzoin, which is an alpha hydroxy ketone. When the hydroxyl group of benzoin is oxidized, we get a 1,2-diketone, which is Benzil. For another quick side note, most procedures I've found call for using 80 milliliters of 70% nitric acid for this reaction. However, as with the benzoin, I did do a preliminary trial run of this reaction and found that using 70% was a bit aggressive for my liking. Using 60%, however, produced virtually the same yield while eliminating the risk of a runaway reaction. Also, if you remember a few minutes ago, I did say that nitric acid is the ideal oxidizer for this reaction. But that's really only true if percent yield and speed are your biggest priorities. However, the problem with this specific procedure is that it'll always leave a tiny amount of unoxidized benzoin. This impurity is fairly difficult to remove, but I figured it probably wouldn't cause me any real problems. There is an alternative procedure that will reliably yield 100% pure Benzil, but it takes more time and produces somewhat lower yields. This alternative procedure uses ammonium nitrate as an oxidizer along with a copper acetate catalyst. If you choose to go this route using the same 21 gram mass of benzoin I used here, you'll simply need to add 60 milliliters of glacial acetic acid and 10 grams of ammonium nitrate to a boiling flask along with the benzoin. You'd then simply dissolve 1.1 grams of copper acetate in 100 milliliters of water, add that to the mixture, and then heat to a reflux for 2 hours. Anyway, looking back at my reaction here, I went ahead and continued the heating until no more NO2 gas was produced, at which point I cut the heat and the stirring. This resulted in two distinct layers forming in the flask, an upper organic layer containing the Benzil and a lower aqueous layer. The mixture was taken while still very hot and then slowly poured into a large beaker of cold water. Since Benzil is insoluble in cold water, it'll precipitate out almost immediately. By the way, as you can see here, I kept the cold water bath stirring aggressively, and I did this to help form a more uniform dispersion of the Benzil. In my trial run, I instead simply poured the mixture into still water, and this resulted in big clumps of Benzil that trapped a lot of residual nitric acid. Anyway, I then collected the crude product in my Buchner funnel and rinsed it thoroughly with a bit of cold water to try and remove any residual nitric acid. For the next step, I decided to transfer the crude Benzil back to the beaker and rinse it with a large excess of sodium bicarbonate to try to neutralize any excess nitric acid. This step might be entirely unnecessary, as it wasn't part of any of the procedures I read, but I felt like it couldn't hurt, so I decided to do it anyway. The crude Benzil was then scraped directly into a beaker along with 200 milliliters of the 50-50 ethanol ethyl acetate mixture and heated with constant stirring until it had totally dissolved. Upon allowing this to cool to room temperature, thin, long yellow crystals of Benzil began to form, and even apart from the color, these looked very distinct compared to the benzoin crystals. I thought these were the most beautiful crystals that came out of this entire project, so I'm gonna go ahead and let this play out. If you want to skip this and go ahead and get on with the synthesis, feel free to skip to the time shown on screen. After allowing the Benzil to cool to room temperature, I put it in a freezer until it had cooled to around negative 15 degrees Celsius. I then simply broke up the pure crystals, collected them in my Buchner funnel, and then rinsed them thoroughly with cold ethanol. These were then finally transferred to a petri dish and allowed to dry completely. After allowing this to dry completely, I was left with these big, beautiful yellow crystals of pure Benzil. I went ahead and weighed these for a final mass of 18.62 grams, which represents an 88.7% yield from my benzoin and a 64.6% yield from the benzaldehyde. The melting point was around 98 degrees Celsius, which is fairly close to the literature value of 95. However, as I mentioned earlier, it's nearly impossible to avoid a minor impurity of a small amount of unoxidized benzoin when using nitric acid as an oxidizer. This can be confirmed by dissolving a small amount of Benzil and adding a bit of sodium hydroxide. If any unreacted benzoin is present, the mixture will turn purple like you'll see in a moment. However, the overall yield is a lot higher using nitric acid compared with the other methods I reviewed, and so I think it's worth the minor impurity. To be on the safe side though, I did decide to run a TLC on both the benzoin and the Benzil just to get an idea of how significant this impurity really was. I'll go into more detail on this TLC later in the video, but for now, simply look at these two spots. This one is the Benzil, and this one is the Benzoin. As you can see, the separation is pretty good, but a tiny amount of my Benzil sample did move up in line with the Benzoin. This indicates that while my Benzil is mostly pure, there is a definite noticeable impurity of benzoin. The easiest way to remove this is honestly to probably just rinse the crystals with warm water. Benzil is completely insoluble in water, while benzoin has some slight water solubility and would probably be rinsed away. Given that the impurity is so slight, however, I decided to skip it, and at this point, I was finally ready to make some phenytoin. To get started, I began by adding 10 grams of my Benzil to an 125 milliliter flask and set the rest aside for a different project. I then added 6 grams of urea, 60 milliliters of ethanol, and 30 milliliters of 30% sodium hydroxide. I added the sodium hydroxide last, and as you can see, the moment the sodium hydroxide is added, the mixture turns a distinct purple color. This is due to the benzoin impurity in my Benzil, and if your Benzil is 100% pure, you probably won't see any purple color. Anyway, after I'd finished adding all of the sodium hydroxide, I transferred the mixture to a stir plate and stirred the mixture aggressively for a few minutes. During this step, the purple color disappears and the mixture becomes a cloudy yellowish color as the reaction begins. I then transferred the mixture to my hot plate, set it up for a reflux, and cranked up the heat. As the temperature increased, the yellow precipitate dissolved and the mixture significantly darkened. While I do think that some darkening is normal here, I think this is a bit unusually dark and again likely due to my benzoin impurity. Eventually it comes to a boil, and this was held at a reflux for 2 hours to drive the reaction forward. What's happening here is called the Blitz reaction, and it's a classic method used to synthesize hydantoins, which are a class of 5-membered heterocycles with 2 nitrogens and 2 carbonyls. In the first step of the reaction, sodium hydroxide abstracts a proton from one of the 2 nitrogens of urea. This forms a molecule of water along with a strongly nucleophilic carbanion. This reactive carbanion then attacks one of the carbonyls on Benzil, which rearranges, allowing another molecule of hydroxide to abstract the second hydrogen from urea's same nitrogen. This facilitates a few more rearrangement steps that end in a ring closure, forming an unstable intermediate molecule called 4,5-diphenyl 4,5-dihydroxy 2-imidazolone. Further rearrangement of this intermediate results in the migration of the 4-phenyl to the 5 position here, which displaces the 5-hydroxy group as another water molecule. A final electron transfer converts the 4-hydroxyl group to a carbonyl group, leaving a negative charge on the adjacent nitrogen. The result is the sodium salt of 5,5-diphenyl 2,4-imidazolone, which is phenytoin. If you take a look back at the reaction, you'll notice that as the reaction proceeded, the dark color lightened up significantly. After 2 full hours, no further color change was observed, and so I cut the heat and stopped the reaction. I then poured the mixture into a 400 milliliter beaker, and typically here you'd want to first remove the reflux condenser, but somehow it had fused to the flask. Anyway, the mixture was next diluted to around 250 milliliters using distilled water and then passed through my Buchner funnel. The sodium salt of phenytoin is very soluble in water, and so any precipitate would have to be either reaction byproducts or unreacted starting material. The filtrate was next returned to a beaker and then very slowly neutralized using concentrated hydrochloric acid under constant stirring. This final step will protonate the sodium salt of phenytoin, releasing free, barely soluble phenytoin. This step is continued until the pH is around 3, and you also might notice during this step that a lot of thick white gas is produced. While this gas might look scary, it's caused by the gas phase reaction of hydrochloric acid and ammonia, forming ammonium chloride. Ammonium chloride is pretty much harmless, and the source of the ammonia here is the hydrolysis of the urea I used earlier. I then collected the crude phenytoin in my Buchner funnel, rinsed it with cold water, and then transferred it to a dish to dry. Once the phenytoin had dried completely, I scraped it into a beaker and dissolved it in hot methanol. This was then allowed to slowly cool, forming crystals of pure phenytoin. These crystals were shorter than the Benzil crystals, thinner than the benzoin crystals, and for some reason seemed to want to grow on the sides of the beaker rather than the top or the bottom. In any case, I eventually put the beaker on ice to fully crystallize all my phenytoin and then collected the pure product in my Buchner funnel. This was once again transferred to a dish to dry, and once it had dried completely, I weighed my final product for a mass of 7.53 grams, representing a 62.8% yield from Benzil and a 40.6% yield from benzaldehyde. Given the number of steps at this point, I am happy with the overall yield, and if I was to pick one of the 3 steps to try to improve, it would probably be the final Blitz reaction to phenytoin. What makes this final reaction finicky is the formation of the unwanted minor product 3,6-diphenyl glycouryl. The formation of this compound seems to be related to the proportions of urea and hydroxide used, with a benzil to hydroxide molar ratio of 1 to 1.87 being optimal for the formation of phenytoin rather than the byproduct. However, I haven't been able to find any research on how the proportion of urea plays a role here, but I'm assuming a minimal amount is better than an excess. Sadly, at this point I don't really have enough Benzil to do any tests of my own at the moment, but I certainly plan to try someday. Anyway, looking back at my phenytoin, I decided to try a few methods of confirming what I'd made. I first took the melting point and found that the crystals melted around 290 C, which is a bit lower than the literature value. It was, however, way higher than the Benzil I started with, which was reassuring. I then decided to run a quick TLC, which I briefly showed earlier in the video. To do this, I first dissolved a tiny amount of my 3 products, benzoin, benzil, and phenytoin, into a few milliliters of ethyl acetate. If you're curious why there's so much benzoin here despite seeing me use most of it earlier, it's because this is the benzoin from my first trial run, and at this point I hadn't really decided what to do with it yet. Anyway, I then used a capillary tube to add 1 drop of each mixture to a TLC plate and then submerged it into a beaker that contained an 80-20 mixture of ethyl acetate and hexane to act as a mobile phase. When illuminated under UVC light, the entire TLC plate will glow green due to the presence of a fluorescent compound. However, the organic compounds I added to the plate absorb some of this light, and so you can see them moving up the plate along with the mobile phase as little dark spots. Now, the problem with this first TLC run is that the benzil and the benzoin moved along the plate at basically the same rate, while the phenytoin lagged only slightly behind. To try and fix this, I decided to run this a second time using an 80-20 mixture of hexane and dichloromethane, and in this significantly more nonpolar mixture, the separation was a good deal better. Taking a closer look at the plate, you can see that the benzil traveled further with the more nonpolar mobile phase than either of the other samples. This was a good confirmation that I had indeed made benzil, as it should have been the most nonpolar of the 3 compounds. However, there was some bleed from the benzoin spot up in line with the benzil spot and vice versa. This leads me to believe that the benzoin contains a bit of benzil impurity and the benzil contains a bit of benzoin impurity. There was also a bit of tailing that lagged behind the benzoin spot, and I'll chalk this up to some more polar impurities from the thiamine. Also, keep in mind that the benzaldehyde I used here was homemade and not distilled at any point, and that could definitely be the cause of some of these spots. Of the 3 spots, however, the phenytoin was the most confusing to me. You can see that in the first trial, there was a clear separation of another spot out of the phenytoin. I assume this is the 3,6-diphenyl glycouryl, which is slightly more polar than phenytoin, as well as a lot bigger. In the second trial, the phenytoin stretched out into a long smear due to very severe fronting. I'm going to chalk this up to interactions between the phenytoin and the 3,6-diphenyl glycouryl in the highly nonpolar mobile phase, but I really don't know for certain. In any case, I think it's clear that while all my products are mostly pure, they could definitely all stand to be recrystallized one final time at least. So there you have it, how you can make a pharmaceutical from simple paint stripper. If you are at all curious about the biochemistry and history of phenytoin, I definitely recommend looking into it as it is quite a fascinating molecule. In any case, that's all I've got for today. As always, I want to give a big thank you to all my members here on YouTube, as your support is vital in funding the work I do here. I also have videos coming up on what I did with the remaining Benzil and benzaldehyde, and consider giving me a follow if that's something you'd like to see. In the meantime, feel free to stick around for some B-roll footage and a sneak peek at some upcoming projects. Thank you all so much for watching, and I'll see you next time.